Alright, hello, welcome. Today in this video I'm going to be talking to you about Green's theorem and I'm going to be proving it. And then I'm also going to point out something, maybe do an example problem and maybe put a question out to y'all. So last video I talked about Green's theorem and I actually worked a couple of examples with it, and that was where we could kind of equate the path integral to a double integral. Okay, and today I'm going to be proving the validity of this formula. And I think before I start, I want to draw kind of a diagram of what I mean by C and R, just to kind of remind you. Now, to draw this the best, and really kind of to the limitations of this proof I'm going to give you, I'm going to draw a region that has a pretty clear rightmost point, leftmost point, topmost point, and bottommost point. And that will be my region R. And so basically, I'll have something like this, And so this is, I guess, what I've just drawn is C, my closed curve. And I do need to point out that there's a couple of other stipulations on this. This needs to be a simple closed curve oriented counterclockwise. Okay? And it needs to be piecewise smooth. I don't think that we've been coming up with parameterizations for curves that weren't piecewise smooth, so here's my curve C that we're talking about here. We're going to path integrate m dx plus n dy. And then the interior of this is what we're calling R. And so we can double integrate nx minus ny on this region, and they're the same, turns out. So I think what I'm going to do is I'm going to start off, and first I'm going to, show you that just the integral over C of m dx is equal to this double integral of negative my dA. That's what I'm going to start with. Then I'll show you the other one. I'm going to actually show you both of these in this video because in most textbooks and most videos, they're just going to show you one and be like, oh, the other one's pretty similar. But I actually don't think it's that similar. There's a little bit of subtlety into the difference. Like, why is there, a minus here but a plus there? And I will go into that in this video. Okay, so. Okay, first, I'm hoping to show that the integral over C of m dx is equal to the negative of double integral of my dA. Okay? And so I'm going to start by parameterizing curve C. What I'm going to do, I'm going to actually work with both of these expressions and show that they're equal to the same thing. All right, and so I'm going to, let's see. I'm going to parameterize curve C. Okay? So for curve C, I'm going to need to actually split this up into two separate integrals. I'm going to take the leftmost point and the rightmost point and kind of block those off. And then this lower half I'm going to call, make sure I call it the same, C1, and then the upper half I'll call C2. Okay, so I'm going to call this one C1 and I'm going to call that one C2. Okay? And then I'm going to parameterize them down here. I'm going to say that C1, I'm going to say x is equal to t and y is equal to some f of t. Because if you look at this curve and we just ignore the top half, we could write this as y as a function of x. It might not be the type of function that we could write down in terms of functions we're already familiar with, but there is a function out there. And then t is going to run from, let's just say x equals a to x equals b. All right, and so I think that, C2, I'll have x equaling t and y equaling g of t. But, up to the orientation of this curve, if I keep that counterclockwise direction, which I need in order to use Green's theorem, here on C1, the curve is going to go from A to B, but on C2, the curve is actually going to go from, if x is equal to t, then it's going to go from t equals b back to t equals a. And we want these to be kind of like this, we want to have the same bounds of integration so we can eventually squash them together and get ourselves a double integral. So what we're going to do is we're going to look at negative C2. Okay, which is a notation that I don't know if we've used before in the videos, but it is certainly in the textbook and something that you'll see. If you want to, reparameterize your curve with the opposite orientation, you could call it the negative version of the curve. Okay, so negative C2 is going to be x equals t, y equals g of t, and t running from a to b. Right, and so now what I'm going to do is I'm going to say that this integral over c of m dx is going to be, I can just split it into c1 plus c2. Or I guess I'm interested in negative c2, but I'm going to say c1 of m dx plus the integral over negative c2 of also m dx. All right. And then I'm going to say that, let's see. Oh, what is actually going into m? That might be an interesting thing to do. And wait a second, hold on. Yeah, the whole reason that I made this negative was so that I can make this a negative also. Right, because if we also, we know, on our kind of simple path integrals, if we reverse the orientation, that's going to reverse the sign of our integral. Okay, so I want the integral over c1 minus the integral over negative c2. Because if we just added them together, that would give us the whole integral over c. Yeah. All right, now what am I going to do? Oh yeah, what is m actually taking in? So the integral over c1, on c1, t runs from a to b. Really, it's x is what we're going to work with, but since x is t, it's really the same thing. Okay, so from a to b, I'm going to say, okay, m, which takes in an x and a y. Well, along c1, x is equal to t and y is equal to f of t, so I'm going to call it x and f of x, just for clarity. And, okay, yeah, dx. And, if this is troublesome to you, just remember x is equal to t. And then when I go and do the other one, y is going to be equal to t, so it's going to be fine. So minus the integral also from a to b of m of x and g of x along c2 dx. And this, okay, now what I'm going to do is I'm going to say, this kind of looks like what happens after we've applied an antiderivative and subtracted, right, when we're taking an integral. So what if I just kind of wrote it using that compacted notation? A to b of m of x and y as y runs from f of x, or from g of x up to f of x. Okay, and then we are still integrating this dx. And notice that if this is like, wait a second, hold on. Oh, okay. I'm actually, because I decided I was not going to do this and try to, convince you that this was this interior thing was an integral. I think that maybe you could see that that's another way you could proceed. What I'm going to do is I'm going to actually stop here, or maybe, yeah, I'm going to combine these into a single integral, but then I'm going to work on this and show that it's also equal to that same single integral. Okay. So really what I want here is I want to just subtract the integrands. So this is m of x and f of x minus m of x and g of x dx. Then over here, I want to work on this double integral. So this double integral of my dA, and hopefully I'll be able to show that it's like the opposite of this. Okay. Well, let's look at the actual region that we're looking at. We have C1 and C2 parameterized with y as a function of x. So what I think I'm going to do is I'm going to let x run from a to b and y run from f of x to g of x. Okay, so the constants need to go on the outside. We know that from our study of double integrals. So that's going to be x equals a to x equals b, and dx will be kind of on the outside. And then we'll be integrating with respect to y as y runs from f of x to g of x. And we will be integrating the partial derivative of m with respect to y. And, yeah, where does my? Now we know how to take an antiderivative of my with respect to y. It's just going to be m. So m takes in x's and y's, and we're interested in y running from f of x to g of x. So if we actually let y be g of x and f of x and subtract them, using the fundamental theorem, I need a little more room, this is going to be the integral from a to b of m of x and g of x minus m of x and f of x dx. And that is the opposite of what I have here, right? Here I have f minus g, and here I have g minus f. Okay. So I've shown you that this part of the integral corresponds to the negative my. And then what I'm going to do is I'm pretty much going to start over and show you the same thing on the integral of n dy equaling the double integral over r of nx dA. And there will be a little bit of subtlety that won't cause us to have the opposite here. We'll actually have the same. And then after that, I'll go and point out why that's true. So I think what I'm going to do is, with all of this, I have to erase some of my annotations here. We're still going to be interested in it being oriented counterclockwise, so we can leave that. Oh, that's supposed to be C. It's not supposed to be changing, but I think that was supposed to go. And then clear off all this. All right. So for, now I'm going to show you that the integral over c of n dy is equal to the double integral over r of nx dA. All right, and so I'm going to start off with the path integral over c of n dy. And what I'm going to do is I'm going to actually kind of label these spots here. And maybe to avoid, using the same letters for both, I'll say that this is y equals h. And this will be y equals k. So hopefully it will be integrating from h to k, and you wouldn't be confused about me using a and b for the limits of integration on both. So the integral over curve c of n dy, again, we're going to call this one c1 on the left half, and we're going to call this one c2 on the right half. Is that what I wanted? Actually, I did the opposite on my notes, and just so to make sure I'm sticking to my notes, I am going to do it the same way here. It really doesn't matter. I'm going to call that c1, and I'm going to call that c2. So it's going to be the integral over c1 of n dy plus the integral over c2 of n dy. And I need to parameterize these things, so I'll have c1 being, all right, x is going to be a function of y. So x equals f of y, and y is equal to t. I guess I'll call it t. That's how we usually parameterize it. And t is on c1 running from h to k. And then on c2, I'm going to have the same problem I had last time, where, if I kind of just respect the orientation of the curve, I'm going to start at t equals k and go back to t equals h, which I know is less. So I'm going to be interested in negative c2. And this is going to be where x is g of y, and y is whatever it likes to be between h and k. All right. Now, maybe I'll do this a little better than I did last time. Okay, we know that the integral over curve C is the sum of the two pieces that comprise C. But in order to get the same bounds of integration, I need to reverse the orientation of this, which means I need to induce a negative here. So I'm going to say that this is the integral over C1 of n dy minus the integral over negative C2 of n dy. Then this is going to be, yes, parameterize the thing. So it's going to be the integral from h to k of n, and what does n take in? It takes in an x and a y, so it'll be, and I could say f of t and t, but I'll just say f of y and y dy. And yeah, minus the integral from h to k on this one, g of t and t, or g of y and y. dy. Okay. This, I think, is where I want to stop, yeah, and then show that this is equal to what I would get over here if I evaluated the double integral. So the double integral of nx dA. All right, on this one, y is running from h to k, and x is going from g of t to f of t. Okay, so y is running from h to k, x is running from g to f. And we're going to integrate dx and then dy. And then nx is still the partial derivative of n with respect to x. And much like before, I'm going to take the antiderivative of nx with respect to x, and I'm going to get n. And so this is going to be equal to the integral from h to k of n of x and y as x runs from g of y to f of y. Okay. And then when I actually plug these in for x and subtract, I'm going to have the integral from h to k of n of f of y and y minus n of g of y and y. All right, and these are the same, so I'm going to conclude that this is equal to that, right? What I had hoped to show. All right, so I've finished it for you, but it's like, wait a second, what actually happened here? Because you took all the same steps, and one of these induced a negative and one did not. Like, what is really happening here? And I think what I want to show you is, maybe I'll try to, no, I think I can go from here. It has to do with over here, the g was less than the f, right? Or what I was calling g was less than what I was calling f. Kind of in the forward direction. But on the other one, the way I had set it up, I had g of x being on top, with f of x being on the bottom. Okay, and one of these, and really it was the one that needed to become negative c2 because it was going backwards. That was what was happening. And so since, I feel like I'm mungling this, but since it was the opposite, on the x direction, that's why we had that negative, was because we were actually integrating from a lower, or from a higher to a lower. Okay. And I think that's all I'm going to say about the proof of Green's theorem. I might come back and show you the formula for the area, why that works, here in a minute. But I think before I do that, I'm going to just throw something else out there. Something that I definitely should have pointed out in the independence of path video, and that I'm pretty sure I put on the quiz, but forgot to mention in the video, I think. And so for independence of path, I was really focused on, the gradient feature where we can just figure out, or the potential function feature. We can figure out what is a potential function for our vector field, evaluated it at the kind of endpoints that I'm interested in. And, much like the fundamental theorem of calculus, use the fundamental theorem of line integrals and compute some stuff. But what I forgot to mention was, what if we have a really, really bad path? What if I want to, integrate over c, something like 2xy dx plus x squared dy, where c is pretty bad. C is looking like, I don't know, let me think of something really not good. Maybe it's going to start over here at 0, 0, and it's going to go like that. Okay, this is something, I don't know, it does not look like a familiar graph to me. I feel like we have very little hope of parametrizing it, right? And so what we're going to do instead is we're going to say, well, hold on a second. If we think about this, the partial with respect to y of 2xy is equal to 2x. And on the other hand, the partial with respect to x of x squared is also equal to 2x, meaning that the vector field we're trying to integrate over here is conservative. Okay, there exists a potential function. I intentionally chose one that I think you can probably just think of the potential function. It's going to be x squared y, plus some constant. And if we're just going from 0, 0 to, let's say, 1, 0, we could use a different path, right? So, we could use the potential, you could use the potential function and go off of our endpoints, but, we can also, what was I thinking there? Why would I want to do this? This is just one that was on the quiz, and for some reason, I guess sometimes it is actually easier to pass through to t if you have this, and you'd rather let, on one hand we could find the potential function, which in general can be sometimes difficult. Maybe I shouldn't have chosen one that was so easy to find a potential function for. But alternatively, if we can't, or if it doesn't seem like it's happening or whatever, we could just create a new path that is the line segment from 0, 0 to 1, 1. And we could integrate along this curve. And that would be equal to the integral over this curve, maybe C0, of the same thing. And this would be really easy to parameterize because x would be equal to t and y would be equal to 0 as t ran from 0 to 1. Okay, so this is an option that I just want to make sure that you knew that this is an option that you have. Okay, I also want to, I'm gonna end with that, but hold on just a second. Yeah, definitely want to tell you about these area formulas and where they come from. I think I mentioned it in the last video because we computed the area of ellipse up there. And that was actually one of probably the few cases where we would really want to use the path integral to find an area rather than just the double integral because of, I'm just thinking about how you would express an ellipse as a function of x and y. And it might not be, or y is a function of x. The double integral, I don't know. Maybe that was a contrived example. I don't want to spend too much time sitting here and thinking about it. But for the area formulas, we know that in the past, if we had the area of a region R, area was going to be equal to the double integral over R of dA, and specifically 1 dA. And then I'm going to rewrite Green's theorem for you. And so what I'm going to really need to do is, if I want to be integrating 1 dA, and I want to kind of equate it to some sort of path integral around the boundary, what I need to do is find a situation where nx minus my is equal to 1, right? And one of the things, I'll just kind of remind you, because it's been a minute since I've pointed this out, is that what this is this is the integral over c of f dotted with dr, where f is equal to m and n, and m and n are both functions of x and y. Okay, so the idea here is to find something where nx minus my equals 1, and then we can just integrate f dotted with dr around the boundary to find the area. Okay. Depending on this f that I find, that gives me nx minus my equals 1. So the big goal here is to work on nx minus my is equal to 1. Now, in general, there are going to be probably a lot of equivalent formulas for this, but I'll just show you 3 of them. Okay. On one hand, I think the easiest one to think of would be just the situation where nx is equal to 1 and my is equal to 0. Okay, so nx equals 1, my equals 0. So we know that this function f is equal to m and n. So if I take the derivative of n with respect to x, I need to get 1. If I take the derivative of m with respect to y, I need to get 0. This is going to be the simplest such function. Okay? And that would mean that according to Green's theorem, this integral of 1 dA is going to be equal to, over region R, is going to be the integral over closed curve C of f dotted with dr. Okay, well, dr is dx and dy in this case. And, well, hold on. Yeah, as I said, it was true. dr is dx and dy. It's usually when we go to compute those, it does pass through into some function of t. So it's going to be f dotted with dx and dy, so this will be the integral of x dy. That is one of our area formulas. Okay. Alternatively, I could also look at nx equals 0 and my is equal to negative 1. Okay, so we've got 0 and negative 1. Okay. So that would mean that when I take the derivative of the top one with respect to y, I need to get negative 1. I'm just going to say that's negative y, and this will be 0. And so if I dotted this with dr, I'll have negative y dx. And so that's another formula we've got here. The integral over c, the negative integral over c of y dx. Okay. The other one that I think is actually the one we used, and I'm not entirely sure why I would use that one instead of one of these two, which both seem simpler and are equivalent to the area. Maybe I just didn't think through what would actually happen if I did that on the ellipse example I did in the last video, but yeah, that's something for you to think about at home. All right, so what if it was like kind of half and half, right? What if I wanted nx to be a half? Then I would need this one to be negative half. Right? So the partial of m with respect to y is going to be negative 1 over 2, so I think it would be negative 1/2 y. And then the partial of n with respect to x is going to be a half, so I'll just do a half of x. Okay. So when I dot this with dr, I'll have negative half of y dx plus a half of x dy. And we could probably clean this up a little bit and call that the integral over c of, or half of the integral over c of x dy minus y dx. Okay, so that's the third one I've got for you. X dy minus y dx. And those are our area formulas, and that's like where they came from. I threw a bunch of stuff at you in the last video without explaining where any of it came from, and it's a very long video now, but this is all just like where all of this stuff is happening, because all the proofs of these things are all right at your level, so I feel like I really do want to relay them to you. And then the last thing I want, we made it all the way to half an hour, so I've got kind of a question I want to pose. I saw it from the textbook, and I thought it was nice, and this is what I want you to be thinking about. The question is, can you show or explain why, and this is true, that the integral over a closed curve C of f of x dx plus g of y dy is equal to 0, provided that f and g are differentiable and C is, the type of curve that passes all of our requirements. It needs to be piecewise smooth. It wants to be simple in the sense that it's not self-intersecting, and it wants to be closed, like the start point is the end point. Okay. Closed, smooth, and simple. Okay. Why is this true? I'll let you think about that.